Hello, students. Today we're going to be talking about more about stars, but we're going to be discussing how we can find their location. And this is going to lead into our lab activity for today. So, when we look up at the night sky, the human eye can detect literally thousands of different stars. Once you start looking through binoculars or a telescope, you are multiplying the number of stars that are visible to the human eye. With our most powerful telescopes, we can literally see billions and billions of different stars. So if you want to study stars and you're looking up one night and you want to look at the same star the following night, how in the world do you do it? It would be so easy to get lost looking up at the night sky. So astronomers have to come up with a way to help them determine the location of stars. And so that's where we're going to begin here today. I've made reference to the Messier catalog in the past of the top 100 coolest things to see in the night sky. This is actually a map here of the Messier objects identifying the locations. But how do we actually determine the location? It looks kind of like a road map of the sky, but in today's day and age where most people just, talk to their car with their GPS and tell me, how do I get to such and such a location? We don't use maps very often anymore. Maps use a coordinate system, an XY coordinate system to help you find the location of some place. Well, we use something similar to that to plot the location of stars in the sky, except they're not here on planet Earth, so we don't use the same kind of maps. So what we do here is think of this diagram. Imagine that the sky is a dome over us as an individual observer. And to find an individual star, there are certain coordinates that we need to determine to give us a precise location. And we call that altitude and azimuth. Let me explain that a little bit better. The altitude of a star is how high it is above the horizon. And by the way, I want to also add that when we talk about the location of stars, we actually talk about it at a specific time at our location on Earth, because the stars change their apparent location in the sky throughout the night because the Earth is spinning. So we really have to factor in time as a coordinate variable here as well. But we're just going to be focusing on these first two. So the altitude is how high an object is above the horizon. So if we are at the vertex of this angle and we're looking off at the horizon, which is as far as we can see until the curvature of the Earth doesn't enable us to see beyond that, the altitude is an angular measurement. We use protractors to measure the angle above the horizon. That's one coordinate. The next coordinate is the direction, called the azimuth. If we have a compass, we know which way is north, south, east, or west. And the azimuth tells us the compass bearing or the direction, which way to turn in order to look at a certain altitude. So here we go. Here are our two words. Altitude is the angle, again, measured with a protractor, which determines the height above the horizon. So if we're looking, we use a protractor to measure how high we are looking. The azimuth is the angle or the direction from north. So if we're standing on the middle of a compass and we look at 0 degrees, that would be true north. If we're looking 180 degrees, Opposite direction, that would be true south. And we've got 360 degrees to play with. So at any point in time, at our observation time, if we know the altitude and the azimuth of a particular star, we can aim our telescope, right direction, right height, and pinpoint the location of a star. So that's how we can determine the location of star. But I want to also talk about star distances, how far away a star is. This actually will tie into our lab activity today because we're going to be using something called the parallax method, which is a technique that uses similar triangles to calculate the distance to objects far, far away. So if we can't actually use a tape measure to measure the distance, we can use the parallax method. And so I want to briefly go over the parallax method with you, starting with your two eyeballs. We have two eyeballs on the human head, and this enables us to have what's called binary vision, or binocular vision, I should say. Binocular vision. Bi meaning two, ocular referring to the eyes. Binocular vision enables us to see things in 3 dimensions because we're looking at something from 2 different angles where our two eyes are. It enables us and our brains to determine whether something is close to us or far away from us based on the angles of our eyes. Now, we can use this parallax method to help us determine the distances to unknown objects far, far away, distant stars. Let me give you the analogy. Think of your two eyeballs as two positions of planet Earth, and our nose is the sun. Now, if we look at this diagram, the Earth revolves around the sun, and it takes a complete year to do that. If we make an observation to a distant star at one point during the year, and we examine the same star 6 months later, and we examine the same star, then we are viewing it from 2 different angles. And notice this triangle here. We have 2 similar triangles on opposite sides of the sun. We can use mathematics, more particularly geometry, to help us determine the length of this line, which is the distance to the star, because we already know how far away we are from the sun. So if we know this distance, we can calculate this distance if we just simply measure the angle between the sun and the star. And with precise equipment, we have no trouble doing that whatsoever. So this is called the parallax method. Let's take this a step further. We've got a triangle drawn here, and we've got a larger triangle drawn here. We can say that these 2 triangles are similar to one another because they have the same proportions. They're not the same size. This one is bigger than this one, but if they have the same angles, if they have the same 3 angles, then these are proportional triangles, which means if you measured the base of the small one and the base of the large one and the height of the small one and the height of the large one, the ratios would be exactly equal to one another. So we could draw right angles between the base and the altitude of these triangles, and taking measurements, we can make mathematical relationships. So here's the deal. The height of this triangle divided by the base of this triangle is actually equal to the height of this triangle divided by the base of this triangle, because these are proportional or similar triangles. Doesn't matter how small this triangle is or how big this triangle is, ratios are equal to one another. Using that geometric relationship, we've got this equation. A divided by B is always equal to C divided by D. And remember, no matter the size of these triangles, that equation is always true. And so here's what we're going to do in the lab. I want you to look at a top view of our experiment. We are standing over here. Imagine this is your head. Here's your left eye. Here's our right eye. And line B is the distance between your left eye and your right eye. This point here, this red point here, is going to be the end of a ruler which measures the length A of this triangle here between our two eyes and the end of the ruler. You can see that that's a triangle. Now, using the parallax method, we are going to be able to measure the distance to a star on the opposite side of the lab. I'll demonstrate this for you in the lab as we will be blinking our left eye and our right eye back and forth to examine the position of the star on the opposite side of the room as the ruler. So the way we're going to do that is this. We're going to blink our left eye, and we're going to see a measuring. Actually, when we close our left eye and open our right eye, we're going to focus on the star in the back of the lab. And we're going to make sure that the line from our right eye to the end of the ruler to that star is in a straight line. Then without moving our head, we're going to close our right eye and open our left eye. And when we open our left eye, you're going to see a measuring tape on the back wall. That's going to be a big ruler that we're going to be able to measure the distance of this line labeled D from X to Y. And so once we do that, we're going to be able to plug in the values into this equation, A over B equals C over D. And by knowing the values of these different lines, we're going to calculate the distance from the end of the ruler to the star, no matter how far it might be. Now, if you are here today in the lab, we're going to do all the math ourselves. If you're home for some reason, however, I'm going to give you the numbers. And here are the numbers that you can use at home. The distance between our eyeballs is, generally speaking, 0.06 meters or 6 centimeters. The distance of our ruler is 1/3 of a meter or 0.3 meters. The distance that most people get while looking at that ruler in the back of the room is 2.2 meters. And the only number left, X we're going to call it, is the distance from our ruler to the star. So if you do the math, you can set it up. 0.3 over 0.06 equals X over 2.2. And if you simply cross multiply, you'll get 0.06x equals 0.66. Do the math, and your answer is 11 meters. So you can do the math yourself and check that out. But if you're here in person, we're going to do it in real life, and we'll see how close you are to the actual answer. So that's enough of me talking now, because I want us in school to get right to the lab. So until next time, I'll say bye-bye.